very happy to be here today, and as I was yesterday for part of the conference. This piece of research that I'm going to present is the product of H2020 Cortex. This is a EU-funded program for extending the life of nuclear reactors, because as it stands, it's impossible, as the EU says, and other people and other authorities say, to live on other kinds of energy. So unfortunately, or fortunately for countries who have nuclear reactors, it is the only solution. So Cortex, the Cortex program, Horizon 2020, is all about extending the life of nuclear reactors. So we're working with real signals and real situations in this program. Now, this work is a collaboration between Petr Stulik from Hungary, Laurent Pantera from France, and myself. So let's go to the next slide. Okay, and oops. So let's start with what an atom is. I think most of you adapts. So let's start. Oh, there's something written down there. I don't know. I'll like ignore it. So an atom is the smallest unit of ordinary matter that forms a chemical element. So anything that we interact with, either it's solid, liquid, gas, or plasma, is composed of neutral or ionized atoms. Atoms are extremely small. You can see the size. And again, the atom is the smallest unit into which matter can be divided without the release of any electrical charge. It is also the smallest unit of matter that has the characteristic properties of a chemical element. If we go any lower than that, we don't have these properties. So it is the building block of chemistry and also of nuclear reactors. Now, there are two kinds of nuclear interactions that we're interested in. One is fission and the other is fusion. Fission is what we have at the moment. It is the process of splitting a nucleus of an atom in two. And by doing so, you can see on the right picture, on the right-hand side picture, that by doing this, energy is produced. On the other hand, we have nuclear fusion, which is combining atoms in one. This is very, very safe. It's not like nuclear fission, what we have in nuclear reactors. However, the technology of doing this in a grand scale is not there yet. So, nuclear fission is a nuclear reaction, or otherwise it's called radioactive decay process, in which the nucleus of an atom splits into two or more smaller and lighter nuclei. And this fission produces gamma photons and releases, that's what we're interested in, a very large amount of energy, even by the standards that you can see here. Now, what happens is, when an atom collides with a larger atom, it forces it to get excited, let's say, and split into two smaller atoms. So as these are the fission products, and the thing is that there are neutrons that are released during this interaction, which initiate another collision and the fission process to develop. So, and the important thing is that when an atom splits via fission, a huge amount of energy is released. And this is what actually matters, because we want to have plenty of energy and as cheap as we can get it. So now I am showing you a cross-sectional view of the reactor core. The reactor core is where all the interactions take place and the heat increases and so on and so on. So I'll explain a few things that it should be good to know and understand for the following things. So from this view, we can see that we have 8 circles outside the big circle, outside the grid, let's say. And each little circle is an X-core out of core detector. We can also see the grid inside the big square, which contains, and each square of this shape can be either a control rod, a fuel element not currently used, or an in-core neutron detector. The out of core detectors we show with the little circles. So is everything clear up to now? Okay, so the last thing I'll talk about that is more technical is what the control rods do. Now they're the green little sticks that you can see, 3 sticks in each of these 2 figures, and they are used to control the fission rate of uranium or plutonium. And this has to be done in order to control the nuclear reactor. If the rods are out, then fission will continue to take place and it will be unstoppable. And this is when we have explosions and accidents, nuclear accidents. So the control rods are made of boron, cadmium, silver, indium, and so on. And depending on how high up they are or how low they are, they absorb fewer, or more neutrons. Okay, so this is one of the major control parts or aspects of a nuclear reactor. So I think that it's all clear, and you can see, that it can be slowed down or stopped completely, the reactor, by inserting the rods further and further in. Now, in Cortex, we are working with real data, real signals, and at some point we were given a set of 36 in-core neutron signals and 8 X-core neutron signals. This was from a simulation. Now, what I did was I took the 8 signals of the X-core detectors, and the important thing is that the X-core detectors are crucial for giving us information about the state of the reactor. So we can control the reactor by using this X-core nuclear signals. You can see that there are 3, let's say, overlapping parts or sets of detectors. So we can see 1 to 4. You can see there's a pink area. We can see the area 5 to 8 in the cross correlation, which is blue, and these are very high values. And then we can see the other 2 areas that are not colored at all, that the cross correlations are significantly lower. And then you can see a little pink mauve blue square in the middle of this table. And we can see that this is a third formation where, again, the signals are highly correlated. So we can work on signals 1 to 4, 3 to 6, and then again 5 to 8. So we have 3 options which are overlapping, but each one of them is focused upon a separate part or the pink and the blue. They are exclusive of each other. They have exclusive information. They don't share anything. Is everything clear up to now? Okay, I'm carrying on. So it's exactly as I said, we have 3 overlapping areas, and the threshold that was used here was 0.8. It was a very robust threshold. Now, another thing that we will need to understand is the use of 3 tuples of nuclear signals for checking each signal, and also validating the neutron detectors, which are in the core, or in the X core, as we are interested in. So the 3 tuples of NSs, given that there's sufficient, that the signals of these 3 nuclear detectors are sufficiently correlated, they can be used for not only for verifying each other, but for also filling up information on the remaining nuclear signals for which we might not have signals at the time due to failure of a nuclear detector. And we can also validate correct operation of the neutron detectors. And this is also very important, because when something goes wrong, let's say we have 2 signals and they are highly correlated. So what happens to one signal should happen, well, more or less, to the other signal. When we see that these 2 signals are not behaving the same way, which is, the first impression is given to us by the cross correlation, and then we can monitor the signals a bit, and we see that they are not behaving as they should. We can't be sure if this is due to the one of the signals per se, or if it's due to malfunctioning nuclear detector. So this idea of the 3 triple configuration has been found capable of doing both, not only identifying that something is wrong and where it is wrong, but also making sure that are identifying if it is a detector or the signal per se. Okay, so let's go to the next one. Now I'll talk about the tool that I used for this work. This is the harmony theory network. I was my MSc, PhD, and my work now and all through the years is about computational intelligence, artificial intelligence, and swarm intelligence. So the harmony theory network, even though I haven't worked with it for quite some time, was appropriate for this application. It is semantically constructed. It doesn't have nodes which are highly interconnected as other neural networks do, as deep neural networks do as well, but it has 2 layers only, and the connections between the 2 layers are semantic in the sense that the problem is mapped into the characteristics of the problem are mapped. So this is reminds us more of artificial intelligence or programming in general. So map the problem characteristics to the nodes of the network and have the constraints that hold between the nodes as connections between the 2 layers. So this is how the harmony theory network is constructed, and there's only one parameter, the spread parameter, which shows how much each change of a node affects the others. That has to be fine-tuned. In this application, I did not fine-tune it because I got good results with the 0.1 value of the spread parameter. Which was good. And this is nice because you know that the system is robust. It can be further fine-tuned, but you have something that is working well. So we have characteristics in the nodes. The nodes mean something. They are not just passing information through. And the constraints, which are the connection between the nodes, show what is friendly to what. So if one thing is active, one node is active, the other node will also be activated to some extent. Or if one node becomes active, the other node becomes sort of deactivated, or with a decreasing activation. So we have these types of connections, positive and negative, and these are normalized depending on the number of connections from the nodes of the top layer, which we'll see in a minute. So what happens is neural construction, it is purely semantic, and the fitness of the network, the state at which the network is calculated based on the 0 ones of the knowledge atoms and the -1 +1 of the representational features. And this gives us a kind of consensus, what is happening. So how much does the value of each knowledge atom, say, affect the activation of all the representational features, and vice versa? What happens when a representational feature takes a certain value? How does it affect the knowledge atoms? So you can imagine that it's like a pandemonium, because each node, either of the upper or of the lower layer, says something. So when consensus is attained, we know that we have the most harmonious, and this is why it's called harmony theory network, or the solution that is most compatible to the situation here. Is everything clear up to now? Okay, I'm carrying on.
Yes.
Okay, thanks. Wait. Yeah, okay. So for this application, we're going to this application now, and I will talk about the representational features, the nodes of the lower layer. They encode 3 tuples. Wait. Okay, the representational features are encoding all the possible 3 tuples of neutron signals. I think this is clear from what I said before about the nuclear signals and the detectors. So if they're highly correlated above the value of 8, each one of them, each 3 tuple, becomes a node of the lower layer. I think this is okay. I mean, you have read what I have before. Here, let's go to the next slide. Okay. So the representational feature will be active if, let's say, 1, 2, 3 will become active, the leftmost representational feature. It will become active if it is the 3 neutron noise signals, 1, 2, 3. So you see, we have the nuclear detectors 1, 2, 3 in the lower layer, and these correspond to the nuclear signals 1, 2, 3 on the top layer of the network. So if it takes a value of 1, it means that the 3 tuple 1, 2, 3 has checked and says that these 3 detectors and signals are working properly, and the signals are as expected, respectively. If it's -1, it's either I don't know, or it is that something is wrong. So you see, it's quite transparent. Now, the upper layer comprises the knowledge atoms, and each knowledge atom encodes a distinct neutron signal. And each knowledge atom can take 2 values, either +1 if it is active, if node number 1 is active, that means that it is monitored properly. So it is monitored, it is uh, it is a correct signal, and it also means that the corresponding neutron detector is also working well. So by having this representation, if we have all the nodes of the upper layer taking a value of 1, we know that everything is fine with the reactor. If we get fewer values of 1 and some of 0, we understand that there's something wrong. So this is why there's a continuous monitoring in the reactor. Otherwise, we might come, to a problem facing, let's say, an imminent accident. So this is why monitoring is very important. Now, the connections of the harmony theory network are set. There's no training as there is in other neural networks. So it remains constant throughout operation unless we remove a node of either layer. Let's say if we say that neutron detector number 3 is not operating, or we have shut it down, then this node will disappear from the network along with the connections that emanate from it. So I think this is quite clear as well. So with this network now, as you can see it, we can do two kinds of monitoring. One is direct monitoring, as it is encoded in a knowledge atom. So any if node number 1 of the upper layer is active, that means that it is correctly, it's validated and it is correct. So 1, 2, 3, 3 tuples 1, 2, 3, 1, 2, 4, 1, and 1, 3, 4 are okay from the side of detector and signal number 1. And if something is wrong, it's due to one of the other signals or detectors. So this is how this is represented. And we have direct monitoring, which was that signal number 1 can be directly monitored by the 3 tuple of detectors 1, 2, 3. And this is a black line, as you can see. It is the leftmost thin black line. And if we go to the first, the line, the first red line starting from knowledge atom 1 up 1 and down, we go to, let's say, the 3 tuple 2, 3, 4, the fourth node of the lower layer, you can see a red connection, bold connection, which means that it's a positive connection. This is why. It is because 2, 3, 4, the 3 neutron detectors 2, 3, and 4, having signals 1, 2, 3, 4, which are also very highly correlated to signal 1, can monitor this signal as well as the corresponding detector. Okay, is everything clear? Again, it's a bit not complicated, but it has many lines. But if there's any question, please ask. Now, indirect monitoring is all the other, the bold red lines. Oh, I have here the number, it doesn't matter. Direct monitoring here. Yes, okay, so explain that. So there's a certain rule about the number of connections that emanate from each node, but I think this is not that important at the moment. So what is encoded here, it's the same figure, but I'm just explaining, is the 12 sufficiently cross-correlated 3 tuples of neutron detectors in the lower layer, and the 8 captured signals, neutron signals, in the knowledge atoms. And what we're striving for is maximal compatibility between the nodes of the lower layer and the connected nodes of the upper layer. So if everything could be yes, 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 then we would have the perfect network. Unfortunately, it's not always like that. In this case, it could be because we have only positive connections. However, we have a different method of getting the optimal solution, which you'll see in a minute. So there's maximal compatibility, exactly what I said. And one thing I can say, we talked about knowledge atoms, activation values 0 or 1, simulated annealing, representational features -1 or 1, and positive normalized connections. So, okay, now let's go to the procedure of getting exactly what we want, the minimum number of neutron detectors and signals that can be used for monitoring and controlling, observing the entire in-core area. So we start by imposing the activating a single node of the lower layer. So 1 3 tuple. Now, this 3 tuple will propagate its activation value to the upper layer. So the activation value of each knowledge atom of the upper layer will be calculated and thresholded according to some details that are in the paper. And then we will have either an active +1 knowledge atom or an inactive one. And this will then go back again and up, and this is how the network will settle. Now, if, let's say, a representational feature could cover all the knowledge atoms, were connected with all the knowledge atoms, and could establish that there is no problem either with the neutron detectors or with the signals per se, then it would be fine. It would be okay. However, if we look up here, any of the representational features, even the ones which have the most connections, which will be 3, 3, 4, 2, 3, 4, 3, 4, 5, and so on, they cannot activate all of the knowledge atoms. So after the network has settled, and we try this a couple of times, and we see that not all the knowledge atoms are activated, which means that we cannot monitor all the neutron noise signals, we say we stop the procedure and we increment the number of representational features that will be active. So we say a pair, 2 representational features will be activated. Let's see what happens. And so on and so on until we get a solution where all the knowledge atoms, so all the signals and all the detectors, according to what I said before, will be monitored and validated. So it's exactly, I think, what I said. And if you look at this picture, you can see that we have knowledge representational features 3, 4, 5 and 4, 5, 6, because as I said before, we also want to minimize the number of nuclear detectors that will be used, which is valid because we want to work to verify our responses with the other neutron detectors, and we want something that works really fast. We don't want to have to compare many views of what each detector says or what each signal does. So this is why we need a very small number of 3 tuples of neutron signals and detectors in order to monitor the entire set of detectors and signals. Okay, so here I have, we said that it's 3, 4, 5 and 4, 5, 6. These 2 representational features, sets of nuclear detectors, are optimal. And I'll show you this by looking at all the other three tuples of neutron signals, which have the same four numbers, 3, 4, 5, 6, but are different, correspond to different configurations. Now, the cross correlation between signals 3 and 4, it is the first line here, is can be found in this three tuple 3, 4, 5, 3, 4, 6 twice. So the cross correlation is multiplied by 2. And we have the cross correlations in each next column of line 3, 4, let's say. So 3, 4, 5 and 3, 5, 6, this pair of three tuples has this 3, 4 once, and the three tuples 3, 4, 6 and 3, 5, 6 also have it once. The same is true of 3, 4, 5, 4, 5, 6. So, and 3, 4, 6, 4, 5, 6. So we add these cross correlation values. And this is implemented for all pairs of highly correlated neutron signals, which belong to a given three tuple. We don't combine signals from different three tuples. And if we get, so we get all the cross correlations, this is the fitness function of the network for this application. And we can see that we have, it is first, second, third, fourth, fifth, the seventh line where it says HTN fitness. You can see that the highest is for the three tuple 3, 4, 5, 4, 5, 6. It is 0.7997, and there are some other ones which are also good, but not that good, as you will see. So it's 0.7332 and 0.7174. And what happens if you have a look at the occurrence, because this was run, I think, 250 times, and we can see that the 250 times, and you can see that 203 times, and I can show this even better here. So we have 3, 4, 5, and 3, 4, 5, and 4, 5, 6, 3, 4, 5, and 4, 5. So it's the green area. If you look, this is the fitness values that we get, and we have a pie chart with the fitness values, and you can see that green is bigger than the others, but not spectacularly bigger. If you now go to these values here, the occurrence, you can see that it's practically more than 3/4 of the 250 trials. It is the optimal configuration of nuclear detectors. So this says a lot for this settling procedure. So this is, I think, my presentation. So harmony theory networks and other kinds of networks or other kinds of constraint propagation algorithms can be used for online verifying, monitoring, not just a nuclear reactor, but many kinds of systems, even cars. You know, think of car brakes. So it could be used for many applications. I think this is all for now. I don't know if I've exhausted my time or not. So I'm ready for questions.